Hello, this lecture is on implicit differentiation. So you know what differentiation is, and you might remember what the word implicit means in a math class. So far, we've been able to take a derivative dy dx whenever we define y explicitly as a function of x. We have y equals, and then the other side, just terms involving x. An implicitly defined function can be thought of as just an equation with x's and y's kind of all mixed up algebraically. And what we're going to do here is take a derivative of an expression, treating one variable as the independent variable and the others as implicitly functions of that independent variable. So let's take a look. All variables are not created equal. So we have different vocab words for different kinds of variables. We have independent variables, usually x or t. If we're doing trigonometry, we might use a theta or a phi. And then we have dependent variables, right? So usually y is our default choice, but if there's more than one, we might use u or v or w, and there might be some other label if it's an application question, something that makes sense in the context of the problem. Then there's variables which we might call constants, still a letter that stands for a number, but these are considered not to change while the other variables do. And if there's no context of a question, it might be a judgment call to know what's a constant and what's a variable. We'll try to always make it clear. We might use other vocab words like a coefficient or exponent, and these will tell you the algebraic role of the constant, right? Exponent, you know where that goes. Another vocab word you might see is parameter, and that might be synonymous with the word constant. It's a variable that could stand for different values in different possible cases, but it might also be an independent variable itself, if you remember parametric equations. Okay, so the context matters, but keeping those in mind, we can take derivatives. So if I want to take a x derivative of the expression ay, I'll think of a as a constant and y as a function. So the derivative is just a times y prime. But if I write down the x derivative of u times v, I'll think that both u and v might be functions of x, so I'll use the product rule. If you don't know any better, you can just assume that any variable is a dependent variable, and we can write down a derivative of any expression. So if I have x times y squared plus sine of w, well, the derivative of x times y squared using a product rule, it's y squared plus x times the derivative of y squared, and the derivative of y squared using a chain rule is 2y times y prime. Then the derivative of the sine term, again we'll use a chain rule, so it's cosine of w times the derivative of w. And keep in mind that if w actually is constant, that's still true. If w is actually a constant, then dw dx is 0, and so the whole second term here is 0, and that makes sense. The derivative of sine w would be 0 if w was a constant. Now we've got something that looks like a geometry application. So 1/3 pi r squared h is the volume of a cone with base radius r, height h. And we can imagine that the radius or the height might be changing with time, so we can take a t derivative of this. And again, pi over 3 is a constant. You take that out. And otherwise, we're going to take a derivative of r squared h using product rule and chain rule. So 2r r prime is the derivative of r squared, and dh dt is the derivative of h. Okay, so one thing we can do geometrically, we can find the tangent lines of a curve defined by an equation. So if you have an equation with x and y variables, it'll give you a curve in the plane in general. And even though that curve might not be the graph of a function, it might not satisfy the vertical line test, we can take a formal derivative and assume that y is a function of x. And maybe by just looking at one piece of the curve at a time. Okay, so we take an implicit derivative of both sides of an equation. Right? If x x squared plus y squared is an expression, and r squared is also an expression that depends on x, we can take a derivative of both sides. So on the left-hand side, the derivative of x squared plus y squared, it's 2x plus 2y y prime. And the derivative of r squared, we're going to think that r is a constant, so the derivative of a constant is 0. And now we can take this equation and solve for y prime, and we can find y prime is minus x over y. And from the graph, you can see this is telling us the slope of a tangent line of a circle. Okay, so we can see interesting features when we take derivatives. Derivative can be interpreted as an instantaneous rate of change, and when it's on a graph, it's the slope of a tangent line. And just like the case of a function, dy dx will not always exist at every point on a curve. There might be a vertical tangent line. There, the slope is undefined. There might be a cusp or a sharp turn in the graph, and then there's no tangent line. And now that the curve need not be a function, there's one more possibility. The curve might self-intersect. So let's take a look at one nice curve here. X to the fourth is a squared times x squared minus y squared, and that'll give us a bow tie shape. If I take a derivative of both sides of the equation, derivative of x to the fourth is 4x cubed, and the implicit derivative of the right-hand side looks like this, a being treated like a constant. And realize that if y equals 0, then we can't solve for y prime. So we've got 3 points where on the curve where y equals 0, and when x is 5 or minus 5, that's a vertical tangent line. And when x is 0, we've got the self-intersection of the curve. So there's no kind of tangent line when there's two lines crossing each other. On the other hand, we can solve for the horizontal tangent lines. This might be an interesting feature. When y prime is 0, we have a horizontal tangent line. There's one there, it goes all the way across to here, and there's another down at the bottom. And if you plug in y prime is 0 and solve the equation up here, you can say x is plus or minus a over square root 2. And so any point on the graph with those x coordinates will have the horizontal tangent.